This is lesson 4 in module 4 vectors. Here we're going to continue looking at vectors, but we're going to consider vectors in 3 dimensions. In a right-handed coordinate system, the convention is that if you have your x and y vectors, where your x is horizontal and your y is vertical, then your z axis, your third dimension, should be pointing straight out of the page at you. So we have dealt with x and y planes before. The z-axis is there implicitly. It's just pointing out of the page at us. If you have a system that is in 3 dimensions already, it's often conventional to draw the x-axis sticking straight out with the y-axis to the right and the z-axis pointing up. Note that these are consistent with one another. They're just looking at the same vectors, the same axes from 2 different perspectives. But both of them are right-handed coordinate systems, which has to do with the rotations that one gets between these axes. Basically, is your z-axis pointing out or pointing in at you, or pointing out of the page at you, or pointing into the page? Into the page would be a left-handed coordinate system. If we want to define vectors in 3 dimensions, we can use unit vector notation. That's the simplest way to do it. We talked about unit vectors before. We have our x component, and then the I hat unit vector tells us this is the x component. This is how far we go along the x-axis. We have our y component and the j hat unit vector. This tells us that we're in the y direction. This tells us how far to go along that y-axis. And then when we add a third dimension, we have a third component. This is our z component. And k hat is a unit vector that points along the positive z-axis, the same way that I hat and j hat point along the x and y axes. So if you had a vector in unit vector notation, you'd start at the origin. You would go ax along the x-axis. You'd go ay along the y-axis. You'd go az vertically, parallel to the z-axis. And then your total vector A would start at the origin, where your first component started. It would end at the end of the last component, so it would start here, and it would point up and out of the page at us. Another method that we can use to define a vector in 3 dimensions is using spherical coordinates. Capital A here without the overhead arrow is the magnitude of vector A. Phi sub A is the azimuthal angle. That is the angle that rotates in the xy plane about the z-axis. That's the exact same way that we've been defining that standard angle for 2-dimensional vectors. So basically you'd have, here's your x component ax in pink, here's your y component ay in purple, and phi, the azimuthal angle phi, is in the xy plane, and it starts at the positive x-axis and rotates counterclockwise until you get into the direction of vector A, or at least into this A sub xy, which is the component of our vector that is in the xy plane. So we're measuring from the positive x-axis counterclockwise until we're in the direction of the vector. That's the same as our standard angle that we defined in the previous lesson. But when we have vectors in 3D, we need a third parameter to measure a third dimension of motion, and that is theta A. That is our polar angle, also called the inclination. This angle theta starts along the z-axis, and it's measured as a rotation from the z-axis down into the direction of the vector. So notice here you have theta A is the angle between the z-axis and the direction of our vector there. If we want to find relationships here between these various quantities, we can do a couple things. We can say, well, axy is ax squared plus ay squared, because we have a little right triangle here in the xy plane. Ax is in the xy plane, ay is in the xy plane, and axy is that component of our overall vector in the horizontal or the xy plane. And so with this right triangle here, with a right angle between the x and y axes, because these axes are perpendicular, we have this relationship here. And then we have another right triangle. You see, you have a right triangle, a vertical right triangle here with axy in the horizontal plane, az standing straight up, AZ is a vertical line that's perpendicular to the XY plane, and so we have a right triangle there also. And we can say that AXY squared plus AZ squared is A squared, where A is the magnitude of the entire vector that we have there. We can put these two terms in for AXY, and we end up with this equation for the magnitude of the overall vector based on the components of that vector. It looks like the Pythagorean theorem because it is, but you have three terms because really these two are coming from the horizontal component, and you're taking that horizontal component with the vertical component. If you want the azimuthal reference angle, that's phi A, you would use the inverse tangent of the x and y components. In this right triangle here, AY is opposite, AX is adjacent, so we'd use the inverse tangent to find the angle that we have here inside that right triangle, and then you can find the standard angle if you are in the second or third or fourth quadrants. You can also look at this triangle here. This triangle is a little bit more convenient. If this is AXY in the XY plane, we can pick it up and put it up here. It's still parallel to the XY plane. It still has the same length and pointing along a parallel line, so that is an equivalent vector. AZ is the vertical component of the vector. We can align that, pick that up and move it over here and align it with the z-axis, and now we have a right triangle there. If we look sort of in this direction at this right triangle, we'll see that we have AZ is vertical along the z-axis. We've got AXY is horizontal, parallel to the XY plane, and then this side here is A, that is the magnitude of our overall vector. And if this is the z-axis, then theta is an angle that rotates down from the z-axis. So if we want to define this angle, we could use the inverse cosine. If we know AZ, this is adjacent, this is hypotenuse, so we could use inverse cosine to find the angle. If we know all the components, we could use this as the opposite, and that is the adjacent, and use inverse tangent. Note that theta could go anywhere between 0 and 180. 0 degrees of theta would be pointing straight up. 90 degrees of theta would be exactly in the XY plane. 180 degrees of theta would be pointing straight down. So that's why I've omitted the absolute value bars here, so that it accounts for AZ being positive or negative, and that should give you an angle. When you use either of these methods, it should give you an angle. Actually, with tangent, you'd have to find an angle between 0 and 180 if you use cosine. Inverse cosine is defined for theta being between 0 and 180. If you go the other way, if you know theta and phi and the magnitude of the original vector, then what you can do is, if you know theta and you know the magnitude of the vector, you can find the z component, because the z component is going to be the magnitude of the vector times cosine of theta, right? Cosine of theta is adjacent over hypotenuse, as AZ over A, and so we solve for AZ as the magnitude of the vector times cosine of theta. If we take the magnitude of the overall vector times sine theta, that gives us AXY, that gives us this horizontal component in the XY plane. So in these equations here, A sine theta is AXY, that is the magnitude of the vector in the XY plane. Once you have the vector in the XY plane, then you can find the x and y components just like we've seen before. The component in the XY plane times the cosine of theta gives us the x component, cosine of phi gives us the x component, and the component in the XY plane times the sine of phi, this is opposite, so this is the sine of phi, gives us the y component. So these two terms here are sort of like, are a lot like what we've seen before, looking at just the XY plane instead of a vector that's only in the XY plane. And so this was all there was to see. Now this is AXY. This is the component of a three-dimensional vector that is in the XY plane, so this is equivalent to what we've seen before. This is AXY cosine phi, AXY sine phi, just like we saw for vectors in 2 dimensions.